All right, hello, take 3. In this video, I'm going to take you through a problem that uses a proof by induction. The purpose of this video is to simply walk you through this problem at a very slow pace, but also share every single thing that I think about when solving this problem. So that way, A, the proof by induction technique gets solidified in your brain, but B, so you can also pick up on some nuggets of advice or technique that might help you in places that you're struggling with induction or that you can incorporate into your own proofs. With that said, let's take a look at this problem. We're asked to prove by induction that for all n in the positive integers, that this equality holds. The sum from k equals 1 to n of 4k times negative 1 to the k equals 2n times negative 1 to the n plus negative 1 to the n minus 1. This should be a minus sign. Okay. What is induction? If you are unfamiliar with the theory of induction and proof by induction technique, I highly encourage you to read up on it or watch a video. I'm going to just briefly explain the theory of it, but yes. So one way we could solve this problem is be like, okay, I want to show it for all positive integers. So let me show it that it holds true for when n equals 1, my smallest positive integer. So I plug in n equals 1 and do some math and they're equal, yay. Then I'm like, okay, let me show it for n equals 2. And I show it for n equals 3 and so on and so forth. And that would totally work. The only issue is you have to go on forever, and by the time you reach 10 trillion, you'll probably get eaten alive by the sun. So not the best idea, but it could work. Induction gives us a way to circumvent that eons long casework just by some simple techniques. So induction is based off of the idea that if we can show some property, in this case an equality, holds for an arbitrary value k, if that holds, and that influences the property holding true for its successor, the next value in the domain, then it's going to hold true for all values in our domain. Because if this is true, makes this true, then this being true, we could treat k plus 1 to be k. This would also make the next value to be true. And so on and so forth. However, we also need a starting point. Let's just call this n naught, where that's going to influence something ideally, which will lead up to pk. If this does not hold true, then probably none of the rest holds true. But if we can show that this property or equality holds true for some starting point, we can also show a relationship between an arbitrary value k and its successor. Then we have proven it for all values in our domain. It's, a little bit abstract what I'm explaining, which is why I encourage you to read up a little bit on it if you're unfamiliar, but this is just basically the theory. With this comes 3 steps to induction. First is called the base case, where we are ensuring that our property or equality holds true for some very small value, because everything that precedes it or succeeds it here is greater than this n naught. Our second step is called the induction hypothesis, where we are going to make an assumption that our equality or property holds true for some arbitrary value of k. And then the induction hypothesis will come into play into our third step, which is the induction step. We are going to show that p of k plus 1 holds true, but in order to do that, we are going to utilize the information we assumed in our hypothesis. This should hopefully make sense as we do the example. I will point it up as things come along. This is the abstract idea of induction in a nutshell. So let's solve this problem. So, as I just mentioned and conveniently erased, there are 3 steps to induction. The first one being the base case. So, base case, abbreviated BC. What this entails us doing is showing that P naught, or P of n naught, right? That initial value where we're starting this chain reaction of things. Well, if we're proving something for all positive integers, it would only make sense for our starting point to be like the smallest positive integer, because everything that follows is still a positive integer, so we're chilling. So the base case, we will test n equals 1. We want to ensure that the equality holds true to start with, because if it doesn't hold for this, then it doesn't hold for all positive integers, and we've disproven the equality. So we're just going to ensure that it works for n equals 1. So to do this, I'll break it apart into the left-hand side and right-hand side. Let me just move my camera so that way I'm in frame. Good. So the left-hand side, wherever we see an n, we're just going to put the value 1. So we have the summation from k equals 1 to 1 of 4k times negative 1 to the k. This summation has only one term, which is when k equals 1. So this is 4 times 1 times negative 1 to the 1. This is 4 times negative 1, which is negative 4. To show the equality, we also need to show the right-hand side. Again, wherever we see an n, we're going to replace it with a 1. So this will be 2 times 1 times negative 1 to the power of 1 plus negative 1 to the power of 1 minus 1. 2 times 1 is 2 times negative 1 is negative 2. Negative 1 to the 1 is negative 1. Minus 1 equals minus 4. So the left-hand side equals the right-hand side. Our base case checks out. Okay, so now we'll move on to the second step, which, if you recall, is the induction hypothesis. This is arguably the hardest part of an induction proof from a syntactical perspective, but also arguably the easiest part of an induction proof from a mental standpoint of how much energy you have to put into it. Let me clarify what I mean by that. You'll recall when I was giving the theory of induction, I said we want to show P of k influences P of k plus 1, and to do that we'll make an assumption that P of k holds true. We're going to make that assumption in this induction hypothesis, but we just need to word it appropriately. So we're going to assume something to be true. We're going to assume for n equals j, I'm just going to change my variables to j because n is already defined here, and I just want to make an assumption for some sort of value of j. Sometimes we change it to k. In this problem I'm already using k, so I just chose a different value, but you just got to do the change of variables. J shares the same domain as n, and it's also, I guess in this case, greater than or equal to 1. We're going to assume what? We're going to assume this equality. Except now instead of n, we're going to replace it with j. So we're going to assume so this is the assumption we're making. It's just the same thing in terms of j for some integer j. Now comes the induction step. This is where we are going to show the implication. This is our goal. And to do that, we're going to focus our attention on P of j plus 1. We want to show that the j plus 1 case holds true. So our goal is to show basically the same equality except with j plus 1 now. So this is what we intend to show. For now, I'm just going to focus on this left-hand side. So I'm actually going to, no, I can maybe make it fit. So this is sort of my goal. So what do I have to work with? Let's just work with the left-hand side. There are two things you should be having in mind right now. A, we needed to show that implication, that P of j influences P of j plus 1. It makes it to be true. And the second thing, which is related, is we have an induction hypothesis. We have made an assumption that some equality holds true. We better use that. Otherwise, what was the point of assuming it? Right? We did something that seems arguably blasphemous, that we're just taking whatever we want to prove and assuming it to be true for some integer. This is super powerful, whatever we've assumed. We better use it. So, how can I use it? Well, this looks pretty similar to what I have here. The only difference is my bound here is j plus 1, whereas this is j. But I can change this to j by just extracting out the j plus 1th term. So let me make some more space on the board. Voila! So I'm just going to take the summation from 1 to j, and then add on separately the j plus 1th term. So let's write this out. So I've covered the first j terms. Now I'm just going to add on this, but when k equals j plus 1. So now this is what I've assumed up here. That is the left-hand side of my assumption. So I can remove this entire summation and just replace it with the right-hand side, because I've assumed an equality. So this will be equal to 2j times negative 1 to the j plus negative 1 to the j minus 1 plus this term here. So now we're left with this. By the way, this is by the induction hypothesis, this substitution. It's incredibly good to cite that that's what you did, because to a reader who's just reading this proof, this simplification is probably non-trivial, and they would want to see, like, how did you do this? So by letting them know by the induction hypothesis, then, you make the reader happy. So we're left with this expression, which is a bunch of j's and like other things, and which is good because it's kind of starting to look like this, the sum of like these products of things. I don't know. So now it's just a bit of algebra to get what we want. So we see we want this like negative 1 to the j plus 1, and we see that here, and it's almost appearing here. It's just to the j and also here. But let's try factoring it out from all of those terms. So if I factor it from this term, it just becomes 4j plus 1. If I factor it out from here, well, I can take out j of these terms. If I were to take out another one, it would flip the sign of this 2j. So it would be minus 2j. And then same thing here. I can factor out j of them. If I were to factor out another one, it would be minus 1. And then this is the only term I've neglected thus far because it doesn't have this negative 1 to some power. So we'll just throw it on at the end. Let's simplify inside of the parentheses. This is 4j plus 4 minus 2j minus 1, all minus 1. This is equal to 2j plus 3 minus 1. And we're starting to get there, right? This minus 1 is found here and here. We have like a 2 times that kind of floating around in here. It's just that these are kind of separated. So you can imagine this distributing into here. This just requires a bit of algebra, but we can write it as, I'll factor out a 2 from both of these, so it becomes 2 times j plus 1 minus 1. Hopefully I'm still in frame, which I am. It looks so squished because I'm right by a projector screen. I should have brought this up. Did not think about that. Well, that was dumb. Anyways, this is equivalent to that. Now let me factor this into these terms. 2j plus 1 times negative 1 to the j plus 1 plus 1 times that is negative 1 to the j plus 1 minus 1. And that's what we have here. That's the proof by induction. I'm not in camera, so let me get in camera. Nope, wrong way. This way. Yes. That's the proof by induction. It's really just these 3 steps. Base case, induction hypothesis, induction step. What are the key things to take away from this? First of all, know what you're doing, right? Even though there are 3 steps, it's important to understand what am I doing in each step. I'm testing the smallest value to ensure that I have some sort of starting point. I'm making an assumption for some arbitrary value of k, doesn't matter, or in this case for n. I'm just making some sort of assumption. And then I want to show the next value right after this j is true, but I will utilize what I've assumed. Another thing to take away. This was just a mathematical example where it's just an equation and I'm trying to show an equality. Induction can be used for so much more. It can be used for word problems and situational based examples. I didn't have that prepared today, which is why it's important to understand what induction is. This entire idea of showing something for all values in a domain, where in the induction step, we start from this j plus 1 world, and we reduce it down to be in terms of j, which is what I assumed for. I've made it smaller problem, did a substitution with my induction hypothesis, and then resolved everything. So whenever you're doing an induction problem, no matter what it is, if it's math or some sort of situational thing as I explained earlier, these things should be in your mind. That in my induction step, I start with k plus 1. I reduce it downwards. I think about what is changing when I reduce down to k. And then, in this case, we just did some more math and it worked. Sometimes you have to build back up to your k plus 1 or j plus 1 case. There you have to be considerate about how are things influenced when I build back up. It's, again, quite abstract, things that I'm saying out loud, but I assure you with practice it'll make sense. Hopefully some takeaways were made in this video. Hopefully this was helpful. And yeah, I think that's it. Thank you for watching.